Welcome back to Math 104. We now have two ways of testing whether events are independent. The first one, the probability of E given F equals probability of E test for the independence of E and F, makes sense conceptually. Understanding why this makes sense conceptually goes to the heart of understanding what independence is. To say that these two probabilities equal one another, the before the fact and the after the fact probabilities, is the same as saying that the occurrence of F has no influence on how likely we think E is. Has no influence on is the same thing as independent of. But our new test also makes sense conceptually. The test of whether the probability of E intersect F equals the probability of E times the probability of F. Conceptually, the equality of these two numbers does have something to do with independence. Here is a suggestive example to help us understand. About 10% of Rutgers undergraduates are left-handed, because about 10% of the whole population is left-handed. And about 6% of Rutgers undergraduates major in economics. If you find out that a Rutgers undergraduate is left-handed, but you have no other information about him or her, how does this impact your opinion of whether this student is likely to be majoring in economics? So you see somebody writing left-handed. You're sitting on the bus next to them, you have no idea what courses they're taking, you just see them writing left-handed. What does this tell you about this person's status or non-status as an economics major? It tells you nothing. It has no impact on your opinion. And that's exactly how we've been thinking about what independent concretely means. Now a follow-up question. What do you think is the probability that a randomly selected Rutgers undergraduate is a left-handed economics major, and why? We are asking for the probability of the event left-handed intersect econ major. The probability that someone is both left-handed and an economics major. It makes sense conceptually that since 10% of the undergraduates are left-handed, that 10% of the economics majors should be left-handed. And economics majors are 6% of all the undergrads. Therefore, left-handed economics majors should be 10% of 6% of everyone. That is precisely the probability of being left-handed, that's the 0.1, times the probability of being an econ major. That is the 0.06. Thus, it makes sense that the independence of left-handedness and majoring in economics shows up in the equality of these probabilities. This unconditional probability and the product of these two unconditional probabilities. Let's do another example with our new test for independence. A pharmaceutical company has submitted two drugs for approval. It estimates that the first drug, alpha-schmalfidol, which is for headaches, has a 70% chance of approval, while beta-shmetazoline, which is for heartburn, has a 60% chance, and there is a 40% chance that both drugs will be approved. We can ask, is the approval of alpha-schmalfidol independent of that of beta-shmetazoline? We test this by asking whether the probability that both drugs are approved is equal to the probability of A times the probability of B. The probability that alpha-schmalfidol is approved times the probability that beta-shmetazoline is approved. Are these equal? I'm going to write lots of question marks here. I'm writing extra question marks because it is a common mistake to simply write down the equality as an equality. That's a problem because we don't know whether these two quantities are equal. We are testing whether they are equal. We are testing whether the left side really equals the right side. If so, that means that A and B are independent, and if these two expressions are not equal to one another, we will know that A and B are not independent. Why use this approach for testing independence rather than our more familiar one? We don't have to use the new method. We could use the old one, but the new one is actually easier to use because of the way the information is given in this problem. The probability of A intersect B is directly given to us. That is 0.4. We ask whether that is equal to the product of probability of A, that's given to us directly as 0.7, times probability of B, that is directly given to us as 0.6. Thus, every quantity we needed to work with in this formula was given to us directly, which makes this formula quite easy to apply. Now, 0.7 times 0.6 equals 0.42. Does 0.4 equal 0.42? No, it does not. The conclusion is that no, these events are not independent. A is not independent of B. B is not independent of A. The follow-up question here is actually quite similar to the follow-up question we've asked for many other problems. Based on your answer to the previous question, does knowing that beta-schmetazine has been approved make it appear more likely, less likely, or as likely that alpha-schmalfidol will be approved than if we knew nothing about the approval of beta-schmetazine? The fact that A and B are not independent means that this possibility is ruled out. Knowing that beta-schmetazine has been approved does influence our assessment of the likelihood of alpha-schmalfidol being approved. That's what it means that they are not independent. But in which direction is this influence? Now think what probability of A intersect B measures. It measures the likelihood that the events A and B both occur, that the two drugs are both approved. If they were really independent, that probability would equal 0.42. But instead it equals only 0.4. They occur together less frequently than they would if they were independent. Occurring together less frequently means that the occurrence of B makes A seem less likely to occur. Our assessment of the likelihood of A is revised downwards. And when I say less likely, that means less likely than if we knew nothing about B. If this line of reasoning doesn't make sense, if you are uncomfortable with it, you can still do things the old way. The old way means comparing the probability of A given B, the conditional probability A given B, to the unconditional probability of A. That is, compare the after-the-fact probability of A to the before-the-fact probability of A. The after-the-fact probability of A is the probability of A intersect B divided by probability of B. That's just the definition of conditional probability. This equals 0.4, that's the numerator, divided by 0.6, that's the denominator, which equals 2/3, and that's approximately 0.67. Meanwhile, the before-the-fact probability, the unconditional probability of A, is given to be 0.7. So we reach the same conclusion. The new assessment of how likely alpha-schmalfidol is to be approved is less than it would have been before we knew about beta-schmetazine being approved. So by our old method, we reach the same conclusion as we did by our new method. We conclude this set of videos with an important real-life example, something called the prosecutor's fallacy. Suppose that 9 million people live in New Jersey, which is approximately true at the time of this recording, and the perpetrator of a crime is known to be a New Jersey resident. Suppose further that detailed forensic evidence at the scene of the crime implies that only one person in a million fits the description of the perpetrator, based on height, weight, age, hair color, blood type, partial fingerprints, some partial DNA evidence, etc. Finally, suppose that you were on the jury, and there is no dispute in this case that the defendant, the person actually on trial, does fit the description, does fit this one person in a million description of the perpetrator. The defendant, the person on trial, really does have the height, weight, age, etc. that are known to be true of the perpetrator. Now the prosecutor makes the following argument to you, the jury. Here it goes. The defendant fits the one person in a million description of the perpetrator, which we have from forensic evidence. It is extremely unlikely that an innocent person would fit such a detailed description. Therefore, the defendant is overwhelmingly likely to be guilty. Let that sink in for a minute. There are cases in which prosecutors have said something equivalent to this, and from a certain point of view, it sounds very convincing. But we wouldn't call it the prosecutor's fallacy unless it were a fallacy. So how do we understand what's going on? Let's make a two-way frequency table. There are 9 million people in the total population. Of these, one person actually did it. One person is guilty and fits the description. No one is guilty and doesn't fit the description. So there is one guilty person total. How many total fit the description? Think about this for a minute. Fitting the description is a 1 in a million event. Therefore, out of 9 million people, 9 people fit the description. That leaves 8,999,991 who do not fit the description. Now we can figure out how many are innocent in each category. Among those who fit the description, there are 8 who are actually innocent. Among those who do not fit the description, well, that's all of them who are innocent. Our total number of innocents is 1 short of the entire population. Now the moment of truth. Knowing that the defendant does fit the description, what is the probability that he or she is guilty? Is this probability of F given G fits the description given guilty, or the probability of G given F? Guilty given fitting the description. It is the probability of G given F. Why? Because this restrictive phrase, knowing that the defendant does fit the description, limits the set of people we're investigating to the 9 who fit the description. This is probability of G given F. This is the probability of G given F. Given that we're talking about these 9 people who do fit the description, the probability that a randomly selected one of these people is guilty is only 1 over 9. There is one guilty person out of these 9 people who fit the description. That is only about 11.11%. That means that if the prosecutor has nothing else besides the argument that I just paraphrased, then the person sitting in the defendant's chair has only a 1 over 9 probability of actually having committed the crime. That leaves an over 88% chance of not having committed the crime. That is what we call reasonable doubt. The prosecutor's error is to compute the wrong probability, the wrong conditional probability, the probability of F given G complement, the probability that an innocent person, restricting our attention to innocent people, would fit the description. That was the wording. It is extremely unlikely that an innocent person would fit such a detailed description. The probability that given that the person is innocent, they would fit the description is very small. But the probability that given that the person is not guilty, they fit such a description, that is exactly the probability of F given, not G. Fits the description given that they are innocent. This is the wrong thing to compute, and it is conditioning in the wrong direction. This is the right way to condition to answer the question that we are asking. We've seen in this video set that understanding conditional probabilities correctly is crucial for medical understanding. We see that it's crucial for an aspect of legal understanding as well. Here ends video set number 8.